Yeah, so if they give you a series, they give you some series. Okay, you're gone. And I say, does this thing converge? The first thing you check is,
does it converge to zero as a sequence?
So this is what is this?
A series.
That's a series. I can look at the sequence that makes up the elements of the series. And if that sequence is not zero, doesn't converge to zero. So if the limit of this is not zero, then the series diverges. Now, unfortunately, what people do is they don't apply logic rules correctly. They say, okay, if A, then B, so then if not A, then not B. And then they say, okay, if it's equal to zero, then it converges. Yeah, that's bullshit. Right? That's no good. All right, so if it rains, I'll bring my umbrella. If I bring my umbrella, does it rain? No, I'm not magic, right? I brought my umbrella, watch. So logic, you have to be careful. You can't just turn it around. You can't just negate it directly, right? So if this is true, if the limit's not zero, that kicks ass. If my question is, does the series converge and the limit's not zero of the elements, then you're done. It diverges. You're done. But if the limit is zero, what does that mean?
It could converge.
Yeah, cool. So like the very first problem on the quiz, well, the very first one and the very last one were kind of related. Everybody's very first one should have said, given a sequence AN, how would you show it converges? Do I say anything about series? I don't say a word about series. So how do you show that a sequence converges? Take its limit and look at it, right? So that's all I have to do. And as long as that limit is not infinite or oscillatory, as long as it's some finite number, it converges. You guys with me? So a lot of you guys are trying to bring in extra stuff to that question. I didn't say a word about any series. I didn't have to worry about that at all. A lot of you guys are saying I had to check to see if it equals zero. Well, that's one way a sequence could converge. But it can converge to 2. It can converge to 7. And then the last one, I think there were 2 different versions of that.
So as long as it's not asking the series, if the series converges, it has to be zero.
If I give you a problem like this, if I said I know that the limit of AN is 2, right?
That converges to 2.
Does the sum of AN converge?
No.
No.
Of course not. Right? And again, just remember, because eventually this thing gets really close to 2. Right? That's the whole point of this. So eventually this becomes adding 2 forever. That's really all this would become, right? This is adding 2. This is adding stuff that you're really close to 2. So essentially this is adding 2 forever. That's going to go to infinity. It doesn't have a chance. And that's why this whole thing happens. In order for it to possibly converge, this has got to be 0. They've got to get out of their own way. If this is not 0, if it has something left over at the end, then that's going to be infinitely many of those. So even if this thing converges, even if AN really, let's see. So let's say AN converges to like 0.0001. And it converges like this. It converges really slowly to 0.0001. I'm still, at some point, I'm essentially adding 0.0001 forever. And that's going to be infinity. Because you're doing it forever. So the only way you can have a series converge is that the limit is 0. So essentially you're adding 0 forever. All right, so really, one way, this is not a proof or anything, but as long as it goes to 0, as long as my series goes to 0, then possibly at some point it's close enough to 0 that I say it's whatever the hell that sum is, plus essentially 0 forever. So it's going to converge to that. That's not a good enough proof, though. And again, people still, the limit being 0 is not enough. It's just the first check to see if you have to do more work. Right? So that's why basically all of chapter 11, once we talk about that, the rest of chapter 11 is, okay, I need tests. I need tests to see when it converges or not. That's why we have direct comparison. That's why we have alternating series. That's why we have all those tests. Okay, cool. So that's a big one. That's the huge one. That's the one that kills people. But you really have to tell yourself before you start doing a problem, is this a series that I'm working with, or is this a sequence I'm working with? And compartmentalize in your brain what each one is all about. Cool. So anything else?
Could you do one of the two from, or could you do something similar to number 4 on the practice test?
Oh yeah, that's kind of related to this also. And the thing I wanted to check about with that kind of problem, so if I had, for example, there's a problem like this on the practice test. Well, that's the sequence. But let me create a new problem using that. So this will say, does the series the mistake people make, and I can't blame you that much, but this is the part, taking a limit is easy, period. It's related to derivatives. Derivatives are easy compared to any interval. Derivatives are easy. I can always attack it. Taking a limit is easy. It really is, especially that when you remember that taking the limit of tangent, I just take the limit inside. Then it's easy as hell, right? That's easy. I should expect then that the actual work that I have to do is more involved than that. It's interpreting what the hell you just did. So taking the limit of this is easy. The mistake people make is they take the limit of this, they have it come out to a number, and they say, oh, it converges. But if I take the limit of this, am I looking at a series or a sequence? I'm looking at a sequence. In order for the series to converge, the sequence, in order for even maybe to converge, the sequence has to converge to 0. Right? So what do you get when you take the limit of these sequence elements here? Yeah. You get. You can take this inside. So as n goes to infinity, what can I do here? They have the same degree. So it'll be the tangent of. And what's that? I know it's not 0, but still, you got to tell me what the hell it is. That's one reason why I made it come out to be pi over 3. That's one you should know. Yeah, because which quadrant would that be? Fourth quadrant. Tangent's going to be negative. So it'll be negative. Kick ass. Right? Now the important thing is, what was that supposed to be in order for this to possibly be yes? 0. It's not 0, therefore this is, the answer is divergence. So it doesn't converge? No. Divergence. Put an exclamation mark if you want to. Yeah, you have to put that.
Why are we
That's me, I do it.
Why are we able, for tangent, why are we able to just take the limit of the inside?
So these are the little pieces that we forget. And again, I don't blame you because we don't bring it up often enough. But limits, properties of limits, one of them is it can go inside of a continuous function. Okay. Tangent is continuous on its domain. It's got asymptotes in it, right? Tangent's got the little, looks like a cubic with walls and it goes forever in both directions. But it's continuous on its domain. Therefore, the limit can go inside of it. So as long as this function is continuous on its domain, I'm allowed to take the limit of the inside.
That's obviously the same with sine, cosine.
Yeah, exactly. But the funny thing is, I mean, if I ask you, and I remember I did a problem like this, if I said the limit as x goes to 1 of the square root of x plus 1, what is that? Square root of 2. So a lot of you guys are just, no problem at all. But you took the limit inside. You don't even think about it like that. You just freaking put a 1 in for x. Right? But what'd you really do? Did you care about the square root at first? No, you thought, what's 1 plus 1? So you took the limit inside. You did it without even realizing, oh shit, I'm applying the property of limits. Square root's continuous on its domain, I can take it inside. Tangent's the same damn thing for tangent, just like a square root. I can take it inside. Right.
Okay. So you can do the same thing for sine and cosine.
Yes. Sine and cosine are even better. They're continuous and their domain is everything, so they don't have any problems at all. Alright, cool.
So for something that would be convergent series.
So if you are saying that some series is convergent, you must have done a decent little amount of work. Let me say that again. To show that a series converges takes some work, right? Depending on the method you're applying, it takes more or less work. Interval test might take a lot of work, because maybe it's gross to integrate that thing. Geometric series stuff, quick. P-series stuff, quick, right? But you're still not just taking a limit and saying it's 0. You're still applying a little bit more advanced stuff. So if I said, does this converge? Good Lord.
I don't even know what
It's geometric, right?
Geometric, kick ass. Right. Totally geometric.
And are there key components that set you off to that?
Yeah. I'm going to show you, let me rewrite this, but then I want to come back and show you how you don't have to rewrite it like this to figure out the sum. So if you rewrote this a little bit, I could take an extra 9 out. Is that cool?
Yeah.
And then what's left inside, I can do the whole thing to the nth power. So it's repeated multiplication by 9/10. Geometric is all about multiplying by the same thing over and over again. So it's whenever I have numbers raised to the nth power, it could very well be geometric. At least part of it could be geometric. Now if I have like a factorial in another part of it, then overall it ain't geometric. Right? But here, all I got is numbers raised to an nth power. That's geometric. Especially if I can write it like this. So now I know what R is. What's R? 9/10, which is, what's the important thing? It's less than 1, therefore this is convergent. All right, so this might be part A, and part B would be, if it is convergent, what does it converge to, right?
Can we apply that formula?
A minus 1 over R.
Close. You got the parts, just in the wrong place.
A over 1 minus 1?
Yeah. Probably, I'll give that to you.
A just being the first term.
Yeah, A is the first term. So when you look at this, can you guys tell it's 9/10?
Yeah.
What would the first term be if n is 1? What's the first term? You get 81 over 10. So it'll be 81 over 10 over 1 minus 9/10. Or you could pull a 9 out. What would this guy's first term be? Right? I mean, I want you to understand, I'm doing this 2 different ways. Here's one way to do it. Is just see what the first term is, and then 1 minus the repeated multiplier. Right? Yes, ma'am?
Is that an S?
Yes.
Okay.
Sorry.
7.
Not a 5. Even though it still looks like a 5. If I do it this way, it would be 9 times, what's the first term here? 9/10 over 1 minus 9/10. And of course, what's 9 times 9/10? 81/10. I mean, either way you look at it, it's got to come out the same way. And this is really nice because this will be 81/10 divided by 1/10.
81.
Craziness. So if you add that forever, you get 81. That's nifty. Yeah.
So would 1 over square root of 2 to the nth power
Yeah, kick ass. I like it. This is what I love. This is good. This is what you guys gotta be doing. I love that question because you're like, okay, let's explore within this shit. If I do this, what happens, right? So if I add this,
No, two. Sorry, the bottom one only is the end. Whenever
Oh,
it's go to two.
gotcha. Actually, I took a step forward. The beautiful thing about 1 is it is 1 to the end. Do you see what I'm saying? Even if it wasn't a 1, if it was a 4, I could just take a 4 out of the way.
Okay.
So if it was this, it would be 4 times the sum. And I can rewrite 1 over rad 2 to the n as 1 over rad 2 to the n. Because 1 to the n is still the 1 that I would have left in after taking the 4 out. Now what's r?
Whenever it's go to
And is that what it's supposed to be? Yeah, because rad 2 is like 1.4, so that's got to be less than 1. Check, it converges. What does it converge to?
8 over
Yeah, what's the first term? N equals 1?
4 over 2.
4 over rad 2 is the first term. 1 minus the r. Oh, beautiful. Multiply by rad 2, you get 4 over rad 2 minus 1. And you can rationalize that and do all kind of weird shit, or you can just make it into a decimal. I don't care. If you had to rationalize that, if I made you do it, do you remember how to do that?
Multiply by
So 2 plus 1.
Multiply by...
Going 2 plus 1.
Beautiful. The conjugate of this dude. Remember that? The difference of squares, buddy, pair, whatever the hell you want to call it. Rad 2 plus 1. Because that's the idea. You want to have a difference of squares so the middle irrational part cancels. Right? It's always nice when you can cancel the irrational parts. So then you get 4 rad 2 plus 4 over 2 minus 1 is 1. That's kind of nice. Alright, cool. You guys stare at that for a while. So be real careful. I'm glad you brought that up because I don't have to make my R's nice ratios of whole numbers. I can make them whatever the hell I want to make. So if I had this last one of these. I think there was a problem just like that in the homework or something. What would you say about that? Which is greater than 1, so this is divergent. Yes. Yes, sir. Just like that. If R is not less than 1, it's divergent. So it's a knife edge. What about if R was 1? Just do it. If R is 1, what's the sum of 1 forever? Infinity. Don't tell me 1. 1 plus 1 is 1. Add another 1 is still 1. Screw your math, Jeff. That's my math. And I don't want to do this to you too much, but do you see how it's sort of like a P series? That is a knife edge, right? P equals 1, it diverges. R equals 1, it diverges. But what is it for P series now? This is where you got to be careful. That's why I shouldn't have done that. But too bad. It's just the idea that it's a knife edge. Right? So if I have a P series dude, of course that's going to do what? Converge.
The sequence is going to be
The series is going to
converge.
So again, what kind of series is this? P series. And what's got to be true for a P series? If P is greater than 1,
it converges.
The sequence is converged.
series.
Oh.
The sequence will be convergent for a lot of things, right? I mean, I don't want to... If I did give you this, if I said for the sequence 1 over n to the p, I don't want to do that. I don't want to screw you guys up. That could be a problem. But for this to converge, I just need p to not be 0 or less than 0. Think about that for a second. If p equals 0, what is this?
1.
Always. So the limit of this would be 1. The sequence would converge. You with me?
Yeah.
If p is less than 0, meaning it's negative, this would come up. It's going to go to infinity. You guys see that? All right, so enough of that shit, sorry. But again, that's the distinction between sequences and series. So much easier for sequences to converge. Of course it is, because series is adding up all the freaking parts of the sequence. It's going to be harder for that dude to converge. Shit. Yes?
Never mind.
So for this one, of course, this would be convergent. I didn't forget, but it's a little too early to give you that. We got to get it into Taylor polynomials, and then we can talk about that. This guy, and why it's pi squared over 6. It actually converges to that, which is not obvious at all, right? And in his day, Euler was like, big man on campus as far as math went. So he figured that out, and they're like, oh, dude, if anyone's going to figure out, it's going to be you. Shit. And the proof is just freaking awesome. But I'll stop saying that. This guy, we need a new Euler. We need somebody else to come along and help us with that shit. Nobody's figured it out yet. What the hell's that thing sum up to? We don't know. Add is kind of nifty if you think about it too much. Of course, nobody's asking about like 1 over n to the 4th. Yes, ma'am.
Can we do 30 on 721?
Go find someone more comfortable. I don't know. Which one again, sir?
30.
30. Oh, that's, wait. 11 point.
1100.
Thank you, God. Oh, this guy.
That looks like
All right.
It converges.
That ooh sounded like you hadn't seen it before. It's kind of, you don't want to give that away. This is kind of early chapter 11.
No, it was flashbacks to doing the problem.
The whole point of this problem is what has to be true about the power, the P, for this to convert.
More than 1. 0.
And you don't know. I mean, if it was in this form, I could then say something about it. So to be honest, you can start to integrate this thing. And when I say that, you guys are like, oh my God, but does anyone see why this integral is so desperately not hard? This is not going to be a difficult integral. Let me replace it with x's.
because it's a form of ln of x.
Yeah. If I have an ln inside, which sucks. It's kind of like trapped on the bottom. That was trapped inside there, right? So if that was u, is its derivative in there also?
Yeah.
Yeah. Shit, that's the first thing you look for. You rule out u sub, right? U sub totally works here. Because the guy who's trapped somewhere, its derivative is in there with him. So if you let u equal ln, du is 1 over x dx. So I get du. Ln of x is u. Ln of u. And then what can you do? Hey, another one. So like m sub or whatever you want to do. All right. And this is not where you should go, oh my God, it's so hard. No, it's not. Who cares? This is not as difficult as understanding the movie Inception. This is related to it in a way.
That movie wasn't even that difficult.
Huh?
That movie wasn't even that difficult.
Oh shit! I gotta watch it again with a notebook. What are you talking about? I don't know. Where are they at now? Spinning what? What the hell's that thing? So yeah, you'd let m equal that. M would be this, and then you'd have it in this form, wouldn't you? And then you can say what you were trying to say earlier. You can't say it until you get into a familiar form. So you actually don't even have to carry out the integration after that. Once you get it in this form, you can say what we figured out before, that p's got to be greater than 1.
Right.
Maybe. You can't say that for the
So
very
you're saying after you integrate it the second time, you just leave it in the form of m?
Yeah, I haven't really integrated anything yet. I'm just changing the form it's in.
Okay.
And once I do one more, I'll see it's in this form. I'm golden. Then I know it has to be true about the power. Yes, sir.
Can you do 11 1 number 53?
Wait, can you finish this one?
I don't want to. Well, because, I mean, we're there, really. What do I know m equal now?
ln of u.
ln of u. So
Yeah.
dm is?
du over u.
I got you. I'm with you. And so this would be
1 over m.
1 over u du is dm. ln of u is m. So it's in this form. Therefore, the same rules have to apply to that. You can't say that until you get it in that form. And this is kind of more evidence that the ln goes so slow. You have all this multiplication of ln stuff going on, and it still has the same requirements on the p. It doesn't change it at all. That knife edge, it doesn't push it one way or the other. Okay. Yeah.
How does that help us know whether P is greater than or less than?
So we know for this form, the work has already been done. They integrated this and followed through to see what the requirements for this were. And through the integration, you figured out that P's got to be greater than 1. If P equals 1, you get 1 over n, which is, what kind of series is 1 over n? Specifically, very specifically.
It's the harmonic.
Harmonic series, which doesn't converge, it diverges, right?
Yes.
And again, if you integrate 1 over n, what do you get basically? What's the function you get? Natural log. And if you let the ln go to infinity, the inside, it's going to go to infinity. See, so that's why 1 over n is the dividing point. If this power is not 1, if it's 1.00001, then it's not going to be ln shit, right? Not everything's ln. It's going to be power rule. So when you integrate this, you're going to get, I don't know, what are you going to get? So you're integrating n to the negative 1.00, however many zeros you got in there. Okay, so you make it x.
Add 1 to that, and then
Yeah, add 1 to that. What do you get when you add 1 to that?
0.0001, and then over, yeah, that.
And it's negative, sorry. That's the key point. When you add 1 to this, there's still a little bit left over to be negative. I really want you to get this. If it's exactly 1, you get ln. That's going to go to infinity. When it's inside, goes to infinity. If I put this a little bit over 1, I don't get ln. I get x to the negative whatever the amount I went over 1 by. You guys see that? And that is going to go down. So now when I let x go to infinity, this is going to go to 0. And if the integral converges, so does the series. Right? That's the heart of the integral test. Now, why does that make sense? If the integral converges, period, so does the series, because integrals are very much like series. They're adding stuff up forever. That's what the integrals do. If I go to infinity on the integral. You guys see that? That's why that part, integral tests results are so easy to interpret, because integrals are basically versions of series. And we know that. They're built on Riemann sums. They're built on sums. Right? So that's why series and integrals are so closely related. That's why the integral test is actually very simple. What makes it hard is if you have some freaky ass thing inside that's really hard to integrate. And then you go, thank God we got these other tests that are confusing. All right? Okay. So what about the other thing I thought would give people trouble? If nobody has any specific, yeah.
Is there math reduction?
Yeah, there'll be a bonus question. Yeah, so if you don't like math induction, all right, suck, but you're not going to have to. You like that? You're not going to have to do a math induction, but if you like it, I'm going to have one on their bonus. You can give it a try. Yeah.
11 1 number 53. Page 700.
Oh. Ooh, I like that one. Okay, so 53. It's got a nifty. Section 11.1. Does that converge? Is the question. In order to converge, just be a little more formal about convergence. That means that after some point, you'll be so close that you'll be arbitrarily close to what you think it converges to. So if I think this converges to 0, that means forever after some point, I will always be arbitrarily close to 0. That was the whole idea with the epsilon delta proofs that everybody loves, that some of your teachers didn't even show you. Sucks for you, actually. But you'll be all right. So what happens is this always stay arbitrarily close to 0 after some point. The whole idea is 1 0 1 1, 2 zeros 1 1, 3 zeros 1 1, but there will always be that 1. So you'll get to a point where you got 18 trillion zeros just to create a new thing, all right? Because it's so large, nobody's even come up with a name for it, so we'll call it trillion. And you're like, oh, I'm there, 1 shit. Because to be a true limit, you have to always stay within an arbitrary closeness of the limit, whatever it is. And this will never do that. This will always pounce away. I'm there, oh shit, I'm not there. Oh, I'm there, I'm shit, I'm not there. So no, this will not converge. Right? So this is not quite as easy as oscillatory. It's not really oscillatory in the same sense that we think of it. It's sort of like the period keeps changing, but it's still bouncing between 0 and 1. Yeah.
How do we, write that?
Oh, no. No. You're trying to think about how to write it?
You don't?
Like that? Is that what you're
I'm saying, after we write
divergent, you have to explain it.
Yeah, you don't have to write this.
No.
Because that would be
He's asking,
difficult.
to write down. How do we write an explanation as why? Do we
You have to summarize, you have to understand what I just said, and then summarize that. Yeah.
So do we not just say
The easiest way to do this would be to do this, if it's possible, and then take the limit. Do you think it's something you could do? Definitely not easily. Not in any nice form at all that you could attack with the limit easily anyway. So why would you want to do that?
So there's no formula for that?
I'll leave it up to you. But I highly recommend not spending any time looking for it. So you can take that as you. Yeah.
Did we do 11, 5, number 22?
Let's find out. Let's see. Oh.
22.
So this one wants you to graph these. And you can either look up in your manual how to do sequences in your graphing calculator, or whatever calculator you guys are using, or you could just kind of graph a few terms by hand. Right? That's the way I would do this. So 22's got this thing here.
What section?
11.5. What kind of series is this?
Is it geometric?
No? I appreciate that though. Part of it wants to be geometric, but that's not going to be a part of that. It's not playing that, right? So it's not quite geometric.
It's alternating.
Yeah, it's definitely alternating. But the point of this problem is graph some sequence elements and some partial sums. And that's part of what a lot of people messed up on the quiz. If I ask you for the first 4 sequence elements and the first 4 partial sums, I'm asking for A1, A2, A3, A4, and S1, S2, S3, S4. What the hell is S2?
A1 plus
A1.
A1 plus A2, yeah. So it's just the sum so far is what partial sums means. And if you take the limit of these and it converges, that means the series converges, and that's where people freak out. So if I can figure out what Sn is, and I take the limit of Sn and it converges to some finite number, then that means the series converges to that. That's where people really, really mess it up. They start to go, okay, limit being something here doesn't mean it converges, but that's not what I'm saying. This is the sums. The sum by 2 is something. The sum by the third element is this. The sum by the infinite element would be what this is, right? So if this limit comes out to be 7, the sum of this is 7. Because I'm looking at what the sums are. If I'm looking at what the elements are, that doesn't say shit about what the series does. Do you see that? These are just the distinct elements. If I look at this is the sum so far. If I take it to infinity, that's the whole sum. That'll actually be what that is. Let's get back to the point of this problem. I would figure out a few elements. So for example, what's the first element going to be? Positive or negative? Positive, because we negative 1 to the 0. And that'll be 1 over 8. Kick ass. And the next one's going to be negative and positive and negative. The next will be 2 over 64. And then blah, 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 right? And then figure out the sums. And you should try to keep them as fractions if you can. For the purposes of graphing, you make them decimals, right? Okay, cool. I like it. Yes, sir.
So did you say if you figure out on a calculator how to do that, we just write the answer, or you have to...
Yeah, for that problem, it says do it on the calculator, so then you can just kind of roughly sketch what your calculator has, and then give it the answer. You just got to sketch what you can see in your calculator. Yeah. But we don't all have the same calculator, so I'm not even going to go into that.
I got TI-84.
Sweet.
Or if you have website, you just have you put in each
Oh, just
value.
they give you the graph and you put in. Oh, just put the values in.
Yeah, and then you have to like guess the graph.
All right.
It is.
So for a convergent series, you can have something like what will if it's a convergent series, what do the ANs have to do?
Convert.
If it's a convergent series, the ANs have to go to 0. Cool. So if I graph like a convergent series, it might look something like this. For ANs, these are the A's, and then the SNs would look something like S1 would be the same thing as the first two, and then you add those, and you add those, and you add those, and it would come up to something like horizontal asymptote. That's what it would look like graphically for a convergent series. If it's divergent, then there's not going to be any ceiling on the SN. They're going to go to infinity. Right? But if there's a ceiling, that means as n goes to infinity, the sums go to some certain number. That number is the number that the series converges to. Really want that. When you look at these, it's nowhere near enough to say a damn thing about this. The best you can say looking at these is if it goes to 0, this guy's has a chance. If it doesn't go to 0, there's no chance.
You think, are there going to be problems about the specific convergence, I think it is? No,
Conditional convergence?
conditional convergence
Yeah.
and absolute convergence?
So, looking at this dude, let me see.
It will converge. Absolutely.
Conditional convergence means it's kind of a weaker, it makes sense that would be a weaker statement than absolute convergence, right? So conditional convergence says if you leave this in, if you let it alternate, positive, negative, and of course I've already said this a lot of times why that's easier. Sometimes it's subtracting from itself, so it should be easier. So that would mean if this converges as it is, it would be at least conditionally convergent. What would absolute convergence mean?
Take it out.
Do who do what? Yeah, you take, and the beautiful thing about the word absolute is it means both absolute convergence, meaning it's the highest level of convergence, and you use the absolute value, right? You take the absolute value. So if you look at the series after taking an absolute value, how would you show that this converges?
Take a look.
I like this problem, and of course I would, wouldn't I? That might be a bit of a hint for you guys about the test coming up. Let's really look at this bad boy. Do you want to use integral test?
What about direct comparison?
To be honest, interval tests would work really nicely. You buy parts. Well, we won't do that, sure, because I don't want to. So let's say we don't want to do interval.
Direct comparison.
Direct comparison. Because, again, this is coming back to what somebody said earlier. This wants to be geometric in a way. Now, here's the bad part. Do you think this is going to converge or diverge?
Converge.
It wants to.
What do you think?
Converge.
It wants to converge. It seems like.
Yeah.
And think about it. Think about this. If I had, just to not waste time on zeros, if I had this, do I care that this is a billion? I mean, what does this do? What would this series do?
Converge.
It would converge all day long, right? In fact, a billion to the billionth power, to the billionth power, to the billionth power. What? You guys with me? I mean, that I could just take that number out. It's a constant. The sum doesn't care. And then 1 over 8 to the n totally converges, right? So it'll be a big-ass number because it'll be that times whatever that thing is. Now, I really want you to see what I mean. N is 1 at first. 1 over 8 to the n converges. Then it's 2. Well, 2 over 8 to the n converges. And eventually it's going to be this number. Well, that number over 8 to the n converges. Is it ever infinity? No, it never gets to infinity, right? So that's the idea. That's how I know if this should converge. It's not an easy problem to show you the thought process you have to put into it. Because if I want to use direct comparison, what's the very first thing I need to have a feel for?
A ceiling or a floor.
Yeah, a ceiling or a floor, which really depends on, do I think it converges or do I think it diverges? So the thought process here is that's going to be essentially like a finite constant number in a way. That's going to infinity a lot quicker. This should converge. So I suspect this converges, which means I have to find a
Ceiling.
If I think it converges, think about it like this. If I thought it diverged, I want to push it to infinity. So I want to find a floor to push it to infinity. If I think it converges, I want to find something to keep it, down, keep it from going to infinity. So I want to find a ceiling. Does that make sense? Yes. So if I think it converges, I want to find a ceiling. Try to think of something. Convergent starts with a C, ceiling. Divergent, down. Too bad it's not a word that starts with F. It's too bad. Freaking divergent? No, sorry. Suspect convergent, we want to find a ceiling, which means I got to find a sequence that is greater. This is where people freak out. I got to draw that, right? And everybody's like, that's less than, but the sequence I'm about to create has to be bigger than this one. All right. You guys semi with me?
Yeah.
Semi.
N plus 1.
This is what's awesome. You ready? Well, n plus 1 would have the exact same problem. It would be, why did it even do it? It's basically the same form as this. I don't know if you guys remember. Can I just take n away?
Yes.
Can you just put a 1 there?
Yes.
Is this bigger than that?
Yes.
Yeah.
No.
If n is 1, it's the same. But what does n do next? It becomes 2. Is that bigger than that?
No.
Never again. So, not good enough. Come on, I want you with me.
2n
Over
Second.
2n squared plus n. 2n over 8. 2n.
N squared.
N over 8.
You want, now remember, watch. Come on.
8 to the n minus
Remember, if I had this and I couldn't take the 3 away,
n over
what
8
was
to
the
n
alternate
minus
idea?
1.
If I can't just take it away,
Multiply by
I make it like terms,
Oh, yeah.
right? Because then it can get sucked in and I preserve the form of what I know this is trying to be. So I want that to be like terms with that. And this is where people freak out. This is the flexibility you have with inequalities. N is always less than or equal to 2 to the n. That's why I was so hopeful, but some of you guys were saying 2n. It's like, shit. No. We'll let you guys absorb that. When n is 1, and this is 2. When n is 2, n is 2, and this is 4. Holy shit, so that's always true, right? That is the flexibility with these inequalities that you guys are so desperately not used to having. You're so used to working with equalities. Everything has to be exactly equal. Inequalities kick so much ass. They have almost too much flexibility, because then I'll have somebody do this, and what does that do? Diverges. And then like, oh shit. No. See, that, I don't know if you guys get this. The flexibility could take you too far in the wrong direction. You don't want to take that big of a step normally when you're doing this. The very minor step, I don't want to do that. That's up, because it's not true. That is the next kind of step up. That would be like terms with this. It preserves kind of what's going on there. And what does this reduce to?
2/8 or 1/4.
So R is 1/4. Does that converge?
Yes.
Since a bigger thing converges, the smaller dude has to converge by direct comparison. Word it up.
Now from that, if we could figure out what the sum is, right? Yeah.
No, this one you can't figure out what the sum is.
Why that?
Because of that. I can't apply the geometric shortcut because it's not a geometric series.
There's no set R.
I really want you to understand. This series is not geometric, but I compared it to a geometric series that is always larger. Since that one converges, then my small one has a convergence. But do I know anything specific about this? What does it converge to? I don't know. I don't even know if I could figure it out, to be honest. So many of these things you just cannot figure out easily. Right? But we think there's always a way to do it, even though the 1 over n cubed thing is kind of making us look bad. But we don't know. Maybe there isn't always a way to do it. Yeah.
Why wouldn't 2n work? Like, I'm not...
Oh, I really want you to see this. Anything that has this form will have the same problems I had in the first place. So if 2n somehow worked, I shouldn't even have had to do it. Because 2n over 8 is basically this, because I can just put a 2 outside as that. Does that make sense? I have to actually change the form of this somehow. Get rid of something, get something out of the way that was in my way, make something like terms so it condenses to something. So if I see something that wants to be a geometric series, and I use direct comparison, I'm going to try to replace the part that's not with something that is. Because I can do that with inequalities. I have a lot of flexibility with inequalities.
What kind of confused me is that you want to make it greater than the problem you're working on.
Mm-hmm.
And so, yeah, you put a 2n, but what confused me was when you said a 2n, not 2n, a 10n, and you got really big to an extreme.
Yes.
So how do you know when it gets too far? Like,
By the R test.
can you do like 3n or 4n?
It depends on how strong your conviction is about this. If you really know it's convergent, then you can tell when you've gone too far because it won't converge.
Well,
But what sucks is when you're not really sure about that and you go too far and you're like, maybe it diverges, shit. And then it don't, right? So there's no quick answer. I know everybody in the world, not just students, everybody wants to know exactly what to do when. Can't give it to you. Can't. The point I'm trying to make is I try to go little steps I can. So I'm really not changing this that much. I'm just putting it in a different form that I can identify easier. 10 to the n is just stupid. I feel bad saying that, but it just doesn't make any sense. Why would you go way the hell up there, right? You don't want to go very far. 1 to the n doesn't make any sense, so that's 1. So 2 to the n is the next best choice. So you haven't gone that far away from what it was to begin with. Does that make a little bit of sense? I mean, there's just no possible way I could give you exactly like how to tell when you should do this or when you should. There's no way I could do that, right? And it's not. Hopefully, it's not a failure on my part as far as teaching, and I know it isn't. It's just part of how this works. It's part of what math is. Yeah.
Can you choose any number that is less than 8?
Based in this one.
Yeah, you can. Totally. It would all work, right? So if you use 7, it would still work. But again, that kind of opens up more questions as to, well, so that's why I say in general, you try to not take a large step, because then you might take such a large step you've passed the dividing line between convergent and divergent. Right?
As a limit.
Let's say you do what you just did and what you came up with didn't converge, right? Couldn't you do the same thing with something smaller and then that still doesn't converge, then the one above it definitely doesn't converge? If you gave that,
It would be evidence that your first thing was wrong. You could totally be wrong here. And if you're trying to do this and you kind of try everything you can think of and it's not working, then you go, well, shit, maybe it's the other way.
if you get something smaller and that doesn't converge, then what you currently have definitely doesn't converge? You know what I mean?
Oh, I see. No, if totally, obviously, if you make a smaller sequence here
And that doesn't converge, then the one you currently have.
and that diverges, then that's the whole point. If it's bigger and converges, yours converges. If it's smaller and diverges, yours diverges. So totally. And sometimes that'll happen in the process of you trying stuff. You're like, well, that's smaller and it diverged. Oh shit, I'm done. It diverges. I was wrong, but it just proved it diverges. Right. But it's in the process of trying stuff out. And how do you start trying stuff out on this problem is you have a suspicion. That suspicion could be entirely wrong. But in the process of doing this, you might stumble across, oh, it's a smaller dude that diverges. Totally. That'll tell you the actual answer should be divergent. Smaller dude went to infinity. What am I going to do? I'm bigger than him. I'm going to freaking infinity faster. Right?
Is there anything about the remainder estimate you give me on this one?
Yeah, if I do, I'll give you the formula for it. Right? It's just,
You already did the exam?
how do you mean?
Like, you actually know what's supposed to do. You know, you already did the...
Basically, yeah. I'm trying not to give anything directly away. But I'll give you the whole thing with less than equal to blah, blah, blah. Right, I'll give you that. So then you just got to plug and show. You got to be aware of what n is. Right? So if I say find S6, then n is 6. Which means on the other side, it will be n plus 1 to infinity, it'll be 7. The beautiful thing about this is once you integrate this, you've already done that. You just plug in a different limit into it, right? You don't have to do 2 intervals. They're both the same interval, just with a different bottom number. So you did have some of that in your homework, the interval remainder estimate thing. This is technical term, interval remainder estimate thing.
Priscilla?
What's that?
Is that Priscilla?
Yeah.
Definitely not made up.
Let's see. What was I going to say earlier? Shit. Totally forgot. So, one way I would approach studying for this test is using this dude. I tried not to put too much. Let me see. In fact, I put too little. Nice. I know. So you should add to this, like, I don't know why I didn't put this down here.
Which one? The study guide?
Yeah. Obviously, you should know P series, geometric series. I think, like, on number 4, I think I reference problems that have those in it. P series, geometric series. You should know what those two mean and how to tell when they converge and when they diverge, right? And those are relatively simple. What kind of sucks about some of these things, and you'll start to see it even more when we get through the rest of chapter 11, is interpreting the results. Sometimes it has to be greater than 1, sometimes it has to be less than 1. Oh, it drives us crazy. But you just have to try to solidify it in your brain. And then you go, direct comparison. How do you interpret the results? Limit comparison, especially that one. How do you interpret the results of limit comparison? Right? Alternating series is pretty easy, but you got to remember there's 2 parts to that. There's 2 things you got to show me. The 2 requirements for the alternating series. Who thinks they remember what those are?
Continuous.
Continuous increasing and alternating.
Decreasing the limit.
Yeah, so good. So it's decreasing. And the limit So everybody focuses too much on that and say, oh, that means everything converges. And no. If it's alternating and it's decreasing and this, then it converges.
And you test for decreasing by taking the absolute value?
The most direct way to test for decreasing is take the derivative. Now there is another way that the book talks about looking at the a sub n versus the a sub n plus 1th term. So you can do it that way if you want. The book has a few examples like that. I just prefer just taking the derivative straight. Yeah.
But you take the derivative without the alternating piece.
Exactly. Once you identify it as alternating, the rest of this is take the alternating piece out.
Okay.
Just focus on the actual sequence itself, not the plus or minus. But in order to do these, it has to be alternating. Don't apply this to something that isn't alternating. So what sucks is something like this. Doesn't matter. This didn't really suck, does it? Screw it. It doesn't matter. Whatever. So what sucks about a problem like this is this alternating?
Yes.
Not really.
No, it's not. To be alternating as being negative, positive, negative, positive. This is not evenly negatives and positives, right?
Yeah.
As I travel around, and it's going to be radians. It's going to be cosine of 1 radian, cosine of 2 radians, right?
Right.
And so so 1 radian is in the first quadrant, 2 radians in the third, in the second, 3 radians is still in the second. Do you see what I'm saying? Yeah. So it's not going to evenly go between positive and negative. So this is not truly alternating. So what I would attack this with, of course, is direct comparison. Yeah. Because cosine is bounded. You can say it's always less than or always greater than something, right? Than 1 or negative 1. You guys with me a little bit?
Yes.
A little tiny bit? Okay. A little tiny bit. I can take that.
All good. Oh. Converge. It will converge, right?
Yeah, this guy. Well, what do you think? I mean, at the top. Maybe I could have left it like that. I don't know what it is. The top is basically 1 overall. It's like the most the top is. So 1 over n. What does that do?
That converges.
That diverges.
Whatever.
Oh yeah, because.
But this one's interesting actually because you do have this being negative sometimes.
Yeah.
Think about that. We'll see when that comes up.
I think it will converge.
I'm trying to remember what I was going to say earlier. There was something. No, but remember, it's not enough for a series. The limit's 0, sure. But that doesn't mean the series converges. That just means it might converge. The limit of the terms is 0, sure. But the series, I don't know.
I have a question on homework. 11.2, number 18. It gives you certain numbers.
Oh, good. All right, good. All right, so this is one that was on that study guide too. That's a good job. I love that.
Why is it divergent?
I've attained a level. That's awesome. So 18 has this business going on here. Now they're really, really nice to you in this problem. They are so desperately nice to you because they tell you exactly what kind of series this is, which tells you how to attack it. Me, I would give you this and say, tell me if this converges or not. Is this an arithmetic sequence? What does arithmetic sequence rely on? Addition. Subtraction if it's a negative thing, right? So it's not arithmetic because that's -1 and then that's not -1. Is it maybe geometric? What do you multiply 4 by to make it 3? 3/4. And what's 3/4 times 3? Oh, shit. And they told you this is geometric, so you already knew it was based on multiplication going in. So here, I know that R is 3/4. You don't even have to write this. I don't think it tells you to, does it? No. You could if you want to, but there's absolutely no reason to write this in summation form. There really isn't a reason. They don't ask you to. But I'm going to make you to right now, just because. Because I know what R is. I know what the first term is. So I can figure out what it... And why do I know it's convergent, of course? Because it's less than 1. Yeah. But if I wanted to write this in some form...
4 times 3/4 the end.
Yeah, so it starts at 4. Now if I do this, now based off of where I started, I want this to be 4 times 1 for the first term, right? Yeah. You see that? So I got to offset, or it could have made it start at 0 and it could have been n. I don't care, either way.
So then the next question is essentially convergence.
Yeah, so it converges. This is, yeah, that's the one check. What does it converge to? What's the first term?
4.
4. And
4 over 1 over 4.
yeah, so 16. Cool.
16.
Which is just neat. If you think about it, I mean, what does this add up to? I mean, you just ask somebody in a bar, just write this on the napkin, and you'll be like the life of the place. You know, hey, what's this add up to? 16. But yeah, it does. It's neat. It's just weird to look at that and go, that adds up to 16. That's freaky. It totally does. We just proved it. Yeah. Now the next level of all of this discussion would be really seeing how quickly does it get to 16? How quickly does it get to some degree within 16?
Like in units? How many units does it take?
How many elements? How far? S7, S28? That's sort of related to figuring out how quickly computer algorithms work. How quickly do certain sorting methods work. Anybody do computer stuff that would know anything about what I'm talking about? Oh shit, well, I'm talking about programming. Like, yes, good. So you know what I'm talking about. You have searches and they're on the order of n squared or whatever. Yeah. So however long your list is, certain search methods or sort methods take longer based on, you know, what algorithm, what they do to sort. Anyway, that's enough of that. Sorry. Because not many of you are into that. Sean is, so he knows what I'm talking about. All right. Still can't remember what I was talking about. Yeah. Oh, this one, yeah.
Oh yeah.
Is there going to be one like this on the test?
Could be.
Oh yeah, where that's like separate.
Yeah.
Oh wait.
So see, if you look at every other one, you have one sequence that's going 1, 1/2, 1/3, and then you have another sequence that's going 1/3, 1/4, 1/5, right?
Yeah.
All right, let you absorb that for a second. I think we talked about this before, but kind of quickly. And the question is, determine whether this converges or diverges. So what do you think you have to show for this to say something about this whole sequence? I mean, the sequence itself, there's no single representation for the sequence elements. Do you understand what I'm saying? I can write AN for this, relatively easy. I can write AN for this, relatively easy. But AN for everything at once, stop dreaming that hard. Right? So to show that this sequence converges, what do you think it's sufficient to show?
Show both summations.
If each of these converge, right, and this is 11.1, this is only about a sequence. So on one level, this is almost too easy. Because no matter how you look at it, what is each piece of it doing?
It's smaller.
Getting smaller. So the limit is going to be 0. And what you can do is you can write, what would the sum, what would AN form of this be? This is 11.1. This is all about sequence. The sequence of this, right?
One over n.
Yeah, it's just 1 over n. And what would this one look like?
1 over n plus 2.
I'm not going to be all super careful about this is like the even ones and this is all the odd ones. Who cares? These are mine. In fact, I'll call this Bn. So this sequence is A1, B1, A2, B2. Screw trying to keep track of the indices. Let me just go ahead and make it 2 separate freaking sequences. All right, so this sequence is a combination of 2. So if these 2 do 2 things, if they converge and they converge to the same thing, then this sequence converges. Which is actually a very specific application of a general thing of some dude named Cauchy. He studied sequences to death, right? Literally. But anyways, but yeah, if the subsequence of a sequence, if every subsequence of a sequence converges to the same thing, then the whole sequence converges to that thing. Just let that sink into your brain. Kind of makes sense. Is it what? If every subsequence of a sequence converges and they converge to the same thing, then the sequence converges to that thing.
So both have to be.
So I've cut the sequence in half, basically, and both halves converge to 0. Therefore, this sequence converges to 0. Now, if you want to talk about the series, let's not do that. Actually, it won't be too bad. So, yeah.
I'm not totally sure how to word this, so bear with me. But say you're figuring out a sequence like this, and you were able to split it up, so that wasn't necessarily the answer that you were looking for. But if you were able to split it up like this, would you be wrong?
No. Because again, depending on how many terms I give you, because I can give you 50 terms of a sequence, and there could be thousands of possible ideas of what that sequence is, what the next term is, totally all day long. So if you come up with something that works for what I've given you, I must give you credit for that. Which makes grading these really exciting when I get a lot of people figuring out different things. And I'm like, shit, does that work? Yeah, it works, all right. But yeah, I have something specific in mind, and it's normally the most obvious thing, but then I'm like, wow, that's neat. That actually works, what somebody did. That's sweet. But no matter how you break this up, they will still converge to 0, because that's what this sequence wants to do. Yeah. Who has an idea if it was a series, what do you think it would do?
Divergent.
Because what are all the parts based on?
1 over n.
Harmonic, so it looks like it would diverge, yeah. In fact, it's even worse than harmonic because it kind of repeats itself in places, right? So it's like doubly bad.
Doubly.
Totally. Yeah.
Could that be done with telescoping? No.
Telescoping is alternating because the whole idea of telescoping is parts of it cancel out.
Yeah.
There's something related to that with addition, but normally it's like parts fill themselves in, and that's not going to happen here.
Okay.
Yeah, but normally telescoping is alternating so that parts of it cancel out. Yeah. So the most important, best thing you can do for yourself when you're actually taking the test is to take a second before you start doing something and just say, for example, is this a sequence or is this a series that I'm working with? You with me?
Yeah.
People just blow right past that and they go, oh, that's this, and this, and then there. Bam, next one, bam, bam, bam. I'm going to get done with this real fast. You're racing to the F. Don't do that. Go slowly to the higher grade, all right?
Slowly to the n.
Slowly. Yeah. Gotta go to F. At least go slow. Right? All right, officer. I wanted to get to that F. Man, math jokes are even worse than everything. Sorry. Yeah.
So my biggest problem is figuring out when to use the interval test.
Interval test is if you notice what the interval test requires you to do the same thing as you do with direct comparison, right? in a way. You have to have an idea. Well, not really. So, I almost never use integral test unless I see that it's very easy to integrate the thing I'm looking at, right? Or I'm told I must. And you know that there's going to be a section on here where you will be told that you must. I think. I mean, something like, all the examples I can think of are just almost too obvious. But even if I had this, did we have this one earlier? Even if I had that, some of you guys might realize what that really is. But if I told you to use integral, and the reason why if I asked you to do integral test on this that I wouldn't freak out entirely, is what would I use to do this integral? Does anybody see what I would use? Yeah, because I can write this like this, and then it's exactly set up for biparts, right? Your classic biparts, a polynomial piece, a piece that's easy to integrate and differentiate, so it's just sitting there waiting for you to do whatever the hell you want to. Of course, when you differentiate or integrate this, it's going to have a negative sign, right? So you got to be careful. So it's no good answer to that. It's most of the time it could be a different test applied. The nice thing with the integral test is it shows you the connection between series and integration that we knew before, but we want to bring it back now that we're talking about summation stuff in a more general context. We want to bring it back. Can't think of a sequence that I would necessarily have to use integral test. You can pretty much use direct comparison instead of integral test. Yeah.
Could you just take that out and take that out to the end? Because would that actually confirm the divergence?
So u is x, dv is e to the negative x. So what's what's v? Negative e to the negative x. So then it'll be uv minus the interval of the minus and negative cancels v du. So you get negative x e to the negative x minus e to the negative x. And you're actually doing from 1 to infinity, right? So I really should have put little limits in there and blah, blah, blah. So what's the limit as t goes to infinity of... What's the key thing about this problem? When you plug a t in, what's the key thing here? And I think you guys don't pay enough attention to this. Don't go e to infinity is infinity. No, that's not what it says. It's e to the negative x. So it's 1 over
it goes to 0.
Infinity. The whole thing goes to 0, yeah. And remember, the nice thing with the integral test, the reason the integral test's results are easy to interpret, whatever the interval does, the series does, is because the integral is intimately related to the series. They're like the same thing in a way. That's an infinite sum, and what's this? An infinite freaking sum. That's why they made it a giant freaking S. Okay? That's exactly why. I don't know if you knew that. It's a big old sum. Let's make it a big old S. Alright. Left this log shit. Let's make a big old S. Sorry. It's history. It's like the drunk history of math.
You watch that show?
I watched one episode. Didn't really draw me in too much, but
It's pretty funny, actually.
I couldn't fit it in. I have too many other things I'm trying to keep track of. Fuck it out. Anything else?
You said The Walking Dead?
The Walking Dead, yeah.
You watch it again?
Yes. Sucks that now we have to wait forever. I'm sorry if you haven't watched it. I'm not going to see it.
I was worried they were going to leave
Uh-oh.
good things.
Spoilers? Good. All right. Are we good?
No.
You don't have to stay here. It's all right. If you got questions, yeah, apply. It was the 11.5. Yeah. Did you get the one for 11.3, 11.4?
Yeah.
Yeah, I forgot to identify the last thing is the alternating series, and that's 11.5. Yeah.
I know, right?
I've already know how to. So here's the nice thing. If you place n plus 1 with n, and we're used to doing that because sometimes I'd have to put n minus 1, but if I would have started at 0, I could have made it n. So I want to replace n plus 1 with n, then it would be related to. Yeah. So if I make n plus 1 go to n, so right now when I plug a 3 in, I get 4.
Just like
If I replace it with n, I have to start at what? Still make it start at 1. You said something. Yeah, so now make it start at 4, and you can replace it with 1 with 10. And of course you can have that flexibility because all you care about is the right number shows up every time. Right? So n plus 1, that expression depends on where you start. So if you start somewhere else, you can change that expression. Cool.
Yep. So it's just a little bit of the idea it's already confusing.
Oh man, I've had people that actually tested that out. Drum empty, yeah, you can actually smell it on them when we went out and kind of like, oh, that explains the lecture. Not me, personally. I haven't tried that yet.
Oh, man, I've grown up a little bit as far as that. Like, it's not so
Oh yeah, well no, a lot of students will show up. But especially being for the late homework, is that
stuck out
for the tests? Late homework, I mean stuff left over from chapter 7. Turn it in as soon as you can. As soon as I can. The later it is, the worse.
If I want to re-examine geometric series, and what other things are there? Just P series really?
Yeah, the only things we know are P series and geometric series.
Okay, and what section do I want to go to further my understanding?
P series is 11.3.
No, it's 11.3.
Yeah, P series 11.3 because we proved it with the integral test.